in the fully developed region, we get simplifications in the governing equations, and that's why we are able to derive an analytical solution in this region. So let's take a look at the simplifications we get and how that they lead to an analytical solution. So I'm looking in the region where the velocity, the axial velocity is no longer changing in the axial direction. Here's continuity, and there is the axial velocity is no longer changing in the axial direction, so that term has to be 0, which means that term has to be 0. And the implications of that is that the radial velocity can have no gradient in the radial direction, i.e. the radial velocity has to be constant along a line like that, but the radial velocity is 0 at the wall. So we can deduce that the radial velocity is equal to 0. Here's f equal to ma in the radial direction, and since v sub r is 0, the radial velocity is 0, that's 0, that's 0, that's 0, and that's 0, that's 0. That means the pressure gradient in the radial direction is 0, and the implication of that is that pressure is only a function of the axial coordinate. And so this is the f equal to ma in the axial direction, okay? And as I discussed before, the fluid particle can have no acceleration in the axial direction because it's just moving in a straight line at constant velocity, and that's the acceleration, so I can knock that off. And the radial velocity is 0, so that's 0, and there's no variation in the axial direction of the velocity, so I'll knock that off to 0. So what this reduces to is a balance between the pressure gradient in the axial direction and the viscous shear in the axial direction. So if I go to an infinitesimal fluid particle, and so I have the pressure and I have the viscous shear. Okay, that effect of the pressure is given by that term, and the viscous shear is given by that term, and it's a balance between those two terms. This term, it is a function of z, and that term is a function of r, which means that each of these terms has to be constant. And so if you set this to a constant and you integrate it, you'll get the parabolic profile. And because the pressure gradient is constant in the axial direction, it means that when you integrate it, you'll get a linear variation, and the pressure has to decrease in the flow direction because the pressure here has to be greater than the pressure here for the particle to move along like that. So I can predict what the expected trend for the pressure is. So that's going to look like that. So this is z, and that's p. And so just in the fully developed region, I expect the pressure to just linearly decrease. Pardon my chicken scratch here, but I think you get the idea. One thing to keep in mind is that in the fully developed region, the fluent solver will keep all these terms. But they'll come out, the effect of them will be negligible, and you'll basically in that region only these two terms will be significant.